Today we're going to talk about inductors, these solenoids, these coils of wire, and this property they have which is called inductance. And we will compare them with the capacitor. That the capacitor stored energy in an electric field, an inductor is going to store energy in a magnetic field, that the capacitor's electric field had this exponential growth. As more and more charge got here, the field grew more and more slowly. Similarly, the magnetic field will have an exponential growth. The capacitor has this property called capacitance, which was solely dependent on the geometry, and the inductor will have a property called inductance, which is solely dependent upon the geometry. But that will not be immediately clear. The definition of capacitance was the charge per voltage, the voltage between the plates, and you divide that into the charge. That was the capacitance of the plate, and that looks like that's not solely dependent upon geometry. But when we did this work and replaced V by integral E ds and got Q as a function of E and worked it all out, it did come out to be a geometric expression for the various capacitors we dealt with. Similarly, this does not look like it's only geometry. It looks like the inductance depends upon the current, but that's an illusion, okay? That this part here also depends upon the current, and ultimately it divides out. That the symbol for inductance, that equivalent to capacitance, is going to be a capital L. You need to be very careful not to confuse it with this capital L. Indeed, I will put on your worksheet a question: what does that capital L stand for? And that should be a softball. You hit it out of the park. But this is a different L, and we need to be careful from context to know which L you're talking about. This is inductance. As I said before, we in the case of the capacitor, we moved from voltage to this statement about field, and ultimately got the value to go away. Similarly, we can state this flux in terms of field. And so here you have this quantity that depends upon magnetic field, an integral with magnetic field in it. Here's this quantity that's an integral with electric field. Notice once again how when we go from the realm of electricity to magnetism, this charge element flips to the other side of the fraction bar, and this field discussion goes to the other side. That's not really very useful, but I think it's intriguing. Okay. I rather like multiplying through this equation by I to get at this equation, and I've done it out of order. I was supposed to assert that what you have here is flux through each of these loops, and then if you multiply that by the number of loops, that's sort of the total flux divided by the current. Well, there's a name for N phi. It's called the flux linkage. And why did I need to tell you that? Because this rewritten definition of inductance can be read. It's L-I-N and something that looks like a Q. That's read links. Linkage. Links. Ah, that's so good. Now I'm going to remember the definition of inductance. At least that's how Mr. Houghton remembers the definition of inductance. The units of inductance are called henries, capital H. When you write it out, it's lowercase h because you're not talking about the fella. And I would like you to look at this and think about the units of I and the units of flux, magnetic flux. Maybe it would be helpful to have this back. So that would be the units of magnetic field, the units of area, the units of current. So, what are the units of henries in terms of Teslas? And what are the units of henries in terms of joules? I have put that on your worksheet. That may feel like too big a challenge to you, but I think it's doable, and I think it would be a good intellectual exercise for you. So please take that on. If you get frustrated, I will tell you in class. I just need to see evidence that you tried. Okay, now I want to talk about that geometric property of inductance that I referred to. And before I get into that, I need to introduce some new nomenclature. I don't think it's totally new. I think we've done this before. Lowercase n was turns per meter. That's the turn density. I'm going to use a lowercase l for the length of this solenoid, so that it doesn't get confused with a capital L for inductance. And then we have this definition of inductance. And then I will replace the flux by BA. Why can I do that? Well, what's true about, if this is a long inductor, what's true about the magnetic field out here? And the answer is it is 0. And what's true about the magnetic field inside? And the answer is it is constant. And so if you do this integral B dA, and the magnetic field is constant over all of that area, then I think it is quite legitimate to replace the flux by B times A. And then I'll replace N by lowercase n, lowercase l. Not looking so good, Mr. Houghton. And then I'm going to replace the B by the value that I know that B has for a long solenoid. There's the boing. Now I can multiply. I can divide both sides by L. Have you not? I divided by I, it's gone. N times N, that's N squared, and then an A. And there, I think, is a lovely mnemonic. We've got a mnemonic for inductance. But here is a mnemonic for finding the inductance of a solenoid. And you can say it. It says, La Luna. And after all, what are these things? It's a bunch of little moons. La Luna! Oh yeah, sure. It's mine. Don't try to take it away. Okay, now here is some serious stuff. I am sending current through this coil. And that current flowing in an inductor means that you're going to get a magnetic field. Will you please tell me the direction of the magnetic field, both outside and inside? of that inductor if the current is flowing up through this first wire here. But suppose that current is getting stronger. Well, what does that mean about the magnetic field here? These are all things you are answering on your worksheet. Now, if the current is getting stronger, then the magnetic field is changing, and changing magnetic field means changing flux. And if you have changing flux, what are you going to get? Indeed. But the magnetic field was going in a particular direction, and it's going to be getting stronger in that direction. And remember, there's a negative in that equation for the EMF, and hence the field, and hence the current from changing flux. So the current's going to be going, the EMF is that arises because of that changing flux is going to be going backwards. It's going to oppose this getting stronger. If instead this were getting weaker, then again there would be changing flux here, but the flux would be getting weaker, and so the change in flux would be a decreasing, and that is going to introduce an EMF to oppose the decreasing, and then you get a current, an EMF arising because of that change that tries to keep this current going. That if the current is getting stronger, you get what is called a back inductance, a back EMF that opposes it getting stronger and tries to make the current go the other way, which has the effect of weakening this current. If the current is weakening, then you get an inductance which opposes and would try to make it not get weaker. Please note, the back inductance does not oppose the current, it opposes the change. So if it's getting stronger, it'll try to make it weaker. If it's getting weaker, it'll try to make it stronger. Another name given for this is back EMF, or sometimes it's referred to as choke, that it kind of throttles the circuit and kind of shuts it down, that you're trying to send current through here and the back EMF stops the current from going, it chokes it. Okay. So, here you have your definition of inductance. Here is the way I would prefer to write it. I think I was supposed to ask you to do that. Now, if we take the derivative of both sides of this with respect to time, the inductance, remember, is just due to geometry. Oh, let's go back and look at that. You see this, La Luna? It's got the number of turns per meter, the area, the length. It is only geometry that determines the inductance of an inductor. Even though it looks like it seems to depend upon current, it doesn't. So L is not changing with respect to time. It's determined by the geometry. And the number of turns is not going to change with respect to time. But if we have changing current, we've got changing flux, so that will change with respect to time. Oh, but wait a minute. What is that? What is N? D magnetic flux dt. That's EMF. That's the negative of EMF. Lovely. There it is. You've got the change in the current, and the EMF that you get is in the opposite direction. It goes back. It opposes. It chokes. Okay. You may recall in a previous lecture that we talked about the fact that we were not to talk about EMF when it was arising from a changing magnetic field, and that's exactly what's going on here. And that's still the rules. But what we will instead talk about, this EMF here, we will talk about the EMF across the inductor, not the EMF within the inductor, not the EMF of the inductor, but across the inductor. And thus we dodge the bullet that between here and here, there may be an EMF from some battery that's sending current through there, but there will also be an EMF from the inductor between those two ends. And this is how big it will be. The voltage across the inductor is equal, there's the magnitude of the voltage across the inductor is equal to that, and compare that with the voltage of a capacitor, right? This came from Q, CV, but this was the voltage across the capacitor was equal to this. Oh, look, there's di dt. The L is up top, the Q is down on the bottom. Here it's due to charge, here it's due to current. Not a perfect analogy, but not a terrible analogy either. Okay, thank you.